149 to go. John's looking at it out the hatch window. Engine's tracking, just beautiful.
More than 50 years after we sent humans to the moon, the plan is still to head to Mars, something many astronauts who have flown in space thought we would have already accomplished. The Foundation book series is sci-fi series set in a future where human civilization is a spacefaring society. I learned from reading them that we should work on things that will prolong civilization and reduce the probability of there being a dark age. Combining with my architecture and lighting background, I would like to imagine Mars 2026 daylight design. Because I want to study how to apply daylight design on different potential Phase 1 Mars-related habitat design to benefit the well-being of occupants in the interior living space. So, in this video, I would like to work you through Mars 101. Mars/Earth. Potential habitat. Potential landing site. When we talk about daylight design on Earth, we are talking about designing the process by which direct sunlight and diffuse daylight are reflected, scattered, admitted, and/or blocked to achieve the desired lighting effect with the same set of criteria, which includes sun position, location, climate, building tech, human circadian rhythm. But for the future Mars habitat daylight design, this criteria needs to be updated to include unaccustomed sun position, untouched location, unworldly climate, unpracticed building tech, same human circadian rhythm. While Earth takes precisely 24 hours to complete a single sidereal rotation, Mars does the same in about 25 hours. And humans, this means that one Martian day, aka Sol, is very close to a single day on Earth. For most people, the circadian rhythm is a little longer than 24 hours. So for those people, Mars is a great destination. However, its radiation and its dust storm are the two major factors for daylight design on Mars obstacles. Mars is the closest planet to Earth. In terms of their size, Mars is quite small, with a diameter just shy of the width of Africa. In terms of their orbits, Earth and Mars are also quite different. For instance, Earth orbits the Sun at an average distance of 1 astronomical unit, aka AU. However, Mars orbits at an average distance of 1.5 AU. This means on Earth, one orbit travel makes 1 year, and it takes 365 days. For Mars, one orbit travel takes a Mars year, which includes 668 days on average. Mars's axial tilt is very similar to Earth's, being inclined 25.2 degrees to its orbital plane, whereas Earth's axial tilt is just over 23 degrees. This means that Mars also experiences seasons like spring/summer/autumn/winter. The good things are we have good daylight and abundant solar energy. However, the radiation on Mars is not friendly for human survival. Devon Island is the largest uninhabited island on Earth. It has solar irradiance similar to the solar irradiation on the Martian equator. Except for a brief period in June, the intensity of the Sun on Devon Island never exceeds the solar intensity on Mars. The diagram here shows the solar irradiation by using the Devon Island EPW on Andrew Marsh. Here are some baselines for my Phase 1 architectural habitat conditions. I use various potential Mars habitat architectural designs. According to the different habitat designs, we can categorize them into 3 types, including excavation, 3D printing, and inflating. And looking at this chart, we can tell that every single archetype has its advantages and disadvantages. I choose the North Pole as their possible habitat area based on its long stable sunlight for around 300 days within 680 days, its lack of risk of dust storms, and its abundance of water resource and perchlorate. The solar longitude LS is the Mars-Sun angle, measured from the northern hemisphere spring equinox where LS equals 0. LS equals 90 thus corresponds to the northern summer solstice, just as LS equals 180 marks the northern autumn equinox and LS equals 270 the northern winter solstice. According to Miller et al. 2018 the Mars Climate Database. On the left graph shows in one Mars year, C would have half of a year stable daylight. On the right graph, it shows that in one Mars year, North Pole area would have the least amount of dust storm. The Phase 1 habitat on Mars I choose to study is based on my modified version of AI Space Factory's Martia. There are several reasons why I choose this long cylinder form to start with. First, the vertical volume has more space capacity than the horizontal one. Second, because of longer volume means more facade area, which allows the most amount of daylight. Third, it is also the most efficient way to install a skylight on the top of the building to allow more daylight attaching to multiple floor areas. Having windows on all facades would optimize its daylight effect. We can also amplify daylight entry and block radiation by using the blind system, which can automatically change its angles based on the sun angle. Here are the 4 floor plans showing how these windows would be located. And this diagram shows that if we using a double shell system. This is the solar energy that reaches the Martian surface, at the equator at noon on a cloudless, dust storm-less day. That figure is 593 watts per square meter. This is the engineering efficiency of the panels, their capability to transform solar irradiance into electricity. Highly efficient panels currently in development are at around 44%. Using solar panels is important for the days when there is not enough sunlight on Mars. One thing that I realized through studying my thesis is that designing with daylight on Mars has a lot of uncertainties. But challenges always help our species making progress. Good luck, humans. Live long and prosper.